hello everyone around the world. So today we are going to use a Tektronix scope to debugging the DDR2 memory bus. So the scope we are using is DSA 70000 digital series analyzer. So there is the DDR3 and a whole bunch of software integrated into the scope. We can analyze the different high-speed bus. The bandwidth of this guy is 12.5 GHz with 50 gigasample per second sample rate. The probe I'm using is 5 GHz differential probe. So let's take a look at the device under test. So let's turn on the lamp so that we can take a close look at the current setup. This board, we can see this is the CPU bus, and we have 3 DDR2 memory channels and 3 memory on the board. So first one, second one, the third one. The probe I'm checking is I'm connect to the clock signal on the third memory channel. Okay, so if we go back to the scope screen, we will see, okay, let's zoom in this area. We will see the clock frequency is 364 megahertz. Okay, and if we use normal trigger and the normal scope mode, we will see that this is the signal we captured. Right now I'm going to turn on the Tektronix DPX technology, which means the waveform capture rate will be increased a lot. So that will capture the waveform in a lot of waveform in a really short term. So if we turn on this, okay, we will see there's some intermediate timing distortion on the signal. Let's zoom in this area, move close to this area. We will see, okay, on the falling edge of the clock, it looks like there's some jitter issue. So we trigger here. Okay, so we try to isolate this problem. So I'm going to use advanced trigger function. So let's go to the trigger, and I'm going to use glitch trigger to trigger on this kind of timing distortion. So I switch from A trigger to glitch trigger, and because the frequency is like 364 megahertz, so the period of one cycle is 2.7 nanosecond. Okay, so the half of the clock period is around 1.35 nanosecond, right? So let's change the glitch pulse wise. So that means any signal, if the pulse wise is less than this certain kind of range, we will trigger. So we only trigger on the positive pulse wise. Let's decrease this pulse wise a little bit. So we will see right now I'm using 1.4 nanoseconds. So if I continue decrease this value, finally you will see on the normal DDR signal there's some intermediate short pulse, positive short pulse. This is the trigger point. We can see this is pretty outstanding to show this much narrower than the negative pulse wise, right? And also there's some the timing distortion jitter on the bus. So when continue to go down, finally we see still, if we set the pulse wise like 1.24 nanoseconds and move close to here, we will see, there's some interference. So this will finally cause the system crash during the real application running. So because we have this the DPX tools, we can easily to identify the problem and then set the advanced trigger to trigger this issue. And so I think this is a pretty good example to show how efficient we can use the scope to isolate the issue.